Good morning, good afternoon. This is Mr. Lowe again. This is hopefully Thursday, May 7th. We are going to go ahead and start lesson 12.3 today. So far, again, just at this point, everybody's been wonderful. The ones that are turning in the assignments, you're doing a good job of showing your work and labeling your assignment. It makes my life a lot easier, and I very much appreciate it, so thank you very much. We're going to start 12.3 today with inscribed angles. We're going to first talk about what an inscribed angle is. It's really, really easy. And then we're going to talk about two different theorems. But that's a little misleading because we're actually going to talk about a theorem, three corollaries that we're going to talk about, 1, 2, and 3 that I'm covering up. And then we'll talk about another theorem. So it's two theorems technically and three corollaries. It might sound like a lot, but really it's not that bad. So just follow along here. I think it'll be just fine. All right, so the first thing is what's an inscribed angle? Well, what I've drawn so far, if you remember, is that this is a central angle. Remember this? This is the center of the circle. Its vertex is at the center. Central angle. No big deal. We've learned about this already. So we'll call this point C here. That'll be the center. So this central angle, ACB, has an intercepted arc. I don't think I used that word last time. We're going to definitely use it today. Intercepted arc. The intercepted arc is the arc from A to B. So right here, that's the intercepted arc. No big deal. Okay, right there. Because look, it's in the interior of this central angle, right? It's inside of it. So that's the central angle. But what's an inscribed angle? Well, an inscribed angle is any angle whose vertex is actually on the circle itself. So the way I'm going to demonstrate this or talk about this or describe it is I'm going to think of this right here as a rubber band. Here's a nail. There's a nail in the center of the circle, and this is a rubber band. If you were to take that rubber band and basically drag it back and then nail it on the circle, put another nail on the circle and then let it rest, then you have an inscribed angle. So if you can envision that, like just right and push it back, then let's say that there's our nail. We'll call this point D. Okay, so then the rubber band would do this. All right, it would, it would go to there, and then it would come to here because these have not moved. And for all you Star Trek nerds, it looks like a Star Trek symbol, right? That's sideways. Okay. All right, I kind of messed that up a little bit, but right there it is. So angle ADB is an inscribed angle because its vertex is literally on the circle itself, not inside the circle, not outside the circle. It's on the circle, so it's inscribed. Okay, its point is on the circle. Inscribed angle ADB. But notice that this angle here, ADB, has the same exact intercepted arc, right? So if you think about it, what is this angle right here going to do if you take and move it back? Well, if you compare this angle, the central angle, to the inscribed angle, shouldn't it be smaller? And it will be smaller. In fact, that's what theorem 12.11 talks about. It basically says that if an angle is inscribed, then its angle measurement is half of its arc measure. Notice that, remember that central angles, they were the same. So for an example, we'll go ahead and use this. If this angle measurement right here, let's say we're 80 degrees, and I'm just making that up, but I didn't want it to be 90. So if it's 80 degrees, then this arc measure then would be 80 degrees, because we learned a long time ago that the central angle and the arc measure are the same. But an inscribed angle, then, since you backed it up, right, actually becomes, according to theorem 12.11, it actually now becomes half of the arc measure. So now we know this angle measurement here would have to be 40 degrees. ADB is now a 40 degree angle. So that's what basically this is. So the measure of angle D, if it's an inscribed angle, which it is going to be half of the arc, of the intercepted arc. In this case, arc AB. So it's exactly half. So when you move it back or stretch it back, it becomes half. You take that angle here and you cut it in half. No big deal. Okay? So that's that theorem 12.11. No big deal. All right. Now we have three corollaries. Now, for the sake of time, I have drawn these in advance, and so just to kind of keep the video a little shorter. So corollary number 1 says that if two angles share the same intercepted arc, do you see that we have angle X and angle Y? Angle AXB. Do you see it right here? This angle right here is sharing the same intercepted arc, which is AB, as angle Y is, AYB. They have the same arc, so therefore they are congruent. And that's what corollary number 1 says. If two intercepted angles share the same arc, then they themselves are congruent. No big deal. And that makes a lot of sense. So if this arc measure is 80, this would have to be 40 because it's inscribed. This angle would also have to be 40 because it's also inscribed. So therefore they are congruent because look, they share the same arc. So the rule applies to both of them. No big deal. The second corollary, and this one's even easier, basically says that if a angle is inscribed inside of a semicircle, remember semicircles are half of a circle. So this is the diameter. I've drawn diameter PQ. There's the center. So isn't this a semicircle? So if an angle is inscribed in the semicircle, so let's say the vertex is at R now, then basically what's half of 180 degrees? This is our intercepted arc right here, isn't it? Right here, okay? So half of 180, semicircle, would have to be 90. So this is a 90-degree angle. It makes a lot of sense. So whenever this happens, then we know this has to be a right angle. So P and Q are basically endpoints of your diameter. This has to be a right angle. Makes a lot of sense, I hope. And then the third corollary, and this is the one that is not hard, but maybe the least friendly of all of them, but it's not that bad. And it just basically says that if you have a quadrilateral, does everybody see the quadrilateral? JKLM, it's a four-sided figure. If the entire quadrilateral is inscribed, in other words, if all four vertices of a quadrilateral are inscribed or on the circle itself, and they are, J is on the circle, K, L, M, then we know that opposite angles are going to be supplementary every single time. So if this is 100 degrees, this has to be 80. And again, I'm just making this up, okay? And then let's say this angle right here is, it looks like it's a little bit, so we'll call this one, I don't know, we'll call this one 110 just to be different. So then this one would have to be 70 degrees. Opposite angles are supplementary. And that's what the third corollary says. But remember, all this, the common thread is that all these vertices are inscribed, right? They're actually on the circle itself. And that's what causes all these special properties to kick in. Okay? And then the last one, which is theorem 1212 or 12.12, it's now starting to talk, now it's going to interact tangents with chords. This is really easy. It basically says that whenever a tangent, and I'll go ahead and call this a tangent right here. Okay, there's the point of tangency, and I'll kind of branch it off like this. So it only touches the circle here. And any chord, so I'll just draw a chord. Remember, a chord is a segment whose endpoints lie on the circle. That's the common theme for today. So basically, if you take a chord, which is right here, and you combine it with a tangent, then its measurement is just, again, same as before, 1/2 of its intercepted arc. 1/2 of the intercepted arc. Easy money. So if this is A and this is B, let's say, and let's say this point over here is C on our tangent, then the measure of angle ABC is again 1/2 of the intercepted arc. The intercepted arc is right here. Isn't this arc completely in the interior of our angle? It's all sandwiched, right? Sandwiched inside. So 1/2 of the arc from A to B. It's just half. Okay, so just as another example, if the arc measure from A to B is, let's say it's, I don't know, 90 degrees, then this would have to be a 45 degree. Okay, so if the arc is 90 degrees, then take half, and so the measurement of ABC would have to be, of course, 45 degrees. Okay, so it's just half. All right, just draw another example just to make sure we're okay. So here's the center again. We'll draw this as our chord, no big deal. Then we'll draw this as our tangent. We'll say it skims across the bottom like this. So there's that point of tangency, no big deal. So if I tell you that here's A, we'll put B into here just for the heck of it. We can do whatever. We'll call this C, we'll call this point D, and then we'll call this point E. Okay, so here you have a tangent. Oops, I'm sorry. There we go. So, sorry about that. So we have AC is our chord. We have our tangent ECD. That's our tangent. So again, following the exact same rules, the angle measurement is half of the intercepted arc. So notice that the whole circle in this case is being involved because we have two different angles, right? So if I want to find, let's say that the measurement from A to C is 120 degrees. Just to call it out, okay? We'll just go ahead and say that's 120. Then we know, according to the rule, the theorem, is that the measurement of angle ACE, remember the letters order is important, ACE, okay, would be half of 120 because that's what's intersected inside of this angle. So 1/2 of 120 degrees. So this angle would then be 60 degrees. Now, what else do we know? Let's find the measurement of the large angle here. Let's find the measurement of ACD. That's an obtuse angle, right? So ACD, again, would have to be 1/2 of this arc measure. Well, there's 360 in a total circle. If that's 120, that means that ABC, that arc measure, has to be 200, right? And 40 degrees, because it's a grand total of 360. So 240. So half of 240 would then be 120 degrees. Does it make sense that these add up to 180? Because what's half of 360? 180. The entire circle is being used. So it makes a lot of sense. I hope it does, at least. So there's the basics. I will have your assignment posted today. And if you have questions, email me. And I'll probably give an example or two on Friday. Okay, so look for those photos. Have a great day.